Hello then. Well, we are now at the last presentation of this mini colloquium. So for those who are arriving right now, I am Marcelo Pavanello and I'm running to organize this mini colloquium. It is co-sponsored by Electron Devices Society from the IEEE and the Brazilian Microelectronics Society, which is holding the conference. And it is my pleasure then to welcome the last presenter that we will talk about sorry. So there is no surprise anymore. We will talk about reliability of metal gate high K CMOS devices. It is Dr. Andreas Kerber from Intel in United States. So I'm going to say a few words, not so few, to be honest, to say something about Dr. Kerber. And he received the diploma in physics from University of Innsbruck in Austria in 2001, and a PhD in electrical engineering from TU Darmstadt in Germany with honors in 2004. From 1999 to 2000, he was an intern at Bell Laboratories, Lucent Technologies in Murray Hill, New Jersey, USA, working on the electrical characterization of ultra-thin gate oxides. From 2001 to 2003, he was with Infineon Technologies, assigned to International Sematech at IMEC in Leuven, Belgium, where he was involved in the electrical characterization of alternative gate dielectrics for sub-100 CMOS technologies. From 2004 to 2006, he was with the Reliability Methodology Department at Infineon Technologies in Munich, in Germany, responsible for the dielectric reliability qualification of process technology transfer of 110 and 90 nanometer technology products, memory products, sorry. During that time, he developed a low-cost, fast wafer level data acquisition setup for time-dependent dielectric breakdown, TDB, testing with sub-millisecond time resolution. Oops, here, yeah. So a bit more on Dr. Kerber contributions. From 2006 to 2008, he was working with AMD in Yorktown Heights, New York, and Global Foundries in Malta, and East Fishkill, New York, as a principal member of technical staff of front-end of line reliability research with focus on metal gate and high K CMOS process technology, advanced transistor architecture, and device-to-circuit reliability correlation. From 2008 to 2019, he was with Scorpius Technologies in Albuquerque, New Mexico, working in reliability of silicon photonic devices. And from 2019 to March 2021, he was with ON Semiconductor in Santa Clara, California, working in product quality management of CMOS image sensors for automotive, consumer and industrial markets. Since March 2021, he is with Intel in Santa Clara, California, working on CMOS and interconnect reliability for 3D NAND technology. He has contributed with more than 110 journal and conference publications and presented his work at international conferences, including the IEDM, VLSI, and IRPS. In addition, he has presented tutorials on metal gate high K reliability characterization at IIRW, IRPS, and ICMTS. Dr. Kerber has served as a technical program committee member for the CISC, IRPS, IRRW, IMDM, Infosys DERC, and is a senior member of the IEEE, as well as a distinguished lecturer from the Electron Devices Society. And as a distinguished lecturer from the Electron Devices Society, he has been invited and honored you, as you can observe by his list of contributions, or honored us with his presence today to present on reliability of metal gate high K dielectric devices. So with that, you can see the caliber of the people that is talking to you. Andreas, please, the stage is yours.
Thank you for the introduction, and it's a pleasure to be here. First time in the Southern Hemisphere, and I'm happy to talk about metal high K reliability for CMOS devices. Just see how this works here. Just a brief reminder, the Electron Device Society is sponsoring this event. with the vision of promoting the excellence in the field of electron devices for the benefit of humanity. There's a wide field of interest for the EDS, from theory to experiment, simulation, electron ionic devices, processing, as well as quantum effects and emerging materials. If you're an IEEE EDS member, you have benefits. One of the benefits is these educational events like webinars or the mini colloquium. There's publication and, of course, a lot of networking activities there as well. You can follow EDS on the various social media platforms, Facebook, Instagram, and Twitter, I think, which is now called X these days. So you can follow them. And if you're not already joined EDS, it's a good time to think about it and maybe join today. Just a brief disclaimer before we get started. The opinions here expressed in this lecture are my own opinions and don't necessarily represent the views of my employer, Intel Corporation. The data mostly shown here was collected during my tenure at AMD and Global Foundries, and it's all available in the public domain. Quick acknowledgement before we get started. The collaborators from Global Foundries, many of them I worked with. Some of them are still with Global Foundries, some have already moved on, pursuing other opportunities in the industry. While being at Global Foundries and AMD, we had collaboration with research partners. Most of my work was done at Yorktown Heights, which is the IBM research facility in New York. And also, we were partners with EMEC as part of co-partner members, and colleagues here acknowledged for their contribution to the work. This year, we celebrate the 75th year anniversary of the invention of the bipolar or point contact transistor by Shockley, Pardine, and Breton. That was done at Bell Laboratories. Back since 1947, the bipolar transistor has gone through a lot of innovation. And what you see here, which is from Simon C's book, textbook, I think it's Semiconductor Devices. That's how the point contact transistor looked like back in those days. Nowadays, of course, with integration, it looks far more advanced. Now, after the introduction of the bipolar transistor, there were basically two other major innovations in the semiconductor industry which paved the way for what we are doing these days. The first one was the introduction or the demonstration of the MOSFET device, so the metal oxide semiconductor field effect transistor device. The right hand is a little more stable. It was originally proposed by Lillian in 25, but it took a long time to do a first demonstration of this device. And again, it was Bell Labs which demonstrated the MOSFET device at Align Khan. Big challenge for that device was to control the surface states in the early days. So that's why it took a long time from being an innovation on a piece of paper to an actually demonstration. Right after, or around the time the MOSFET was demonstrated, Jack Kilby at TI, he invented the first integrated circuit. To my understanding, it wasn't a fully monolithic integrated circuit, but it was nevertheless a first integrated circuit. And shortly after Noyce, at that time at Fairchild, he came forward with a true monolithic integrated circuit demonstration, and Noyce being one of the three co-founders of Intel Corporation. Now, since the first introduction of the MOS devices in the late 60s, first commercial implementation in the early 70s, the CMOS technologies then were successfully scaled over many generations. And the scaling of these CMOS technology was outlined through the scaling laws introduced by Bob Denard and co-workers at IBM. So you have basically from the early days where the feature size were in the tens of microns in terms of device length and device width, or less than 100 nanometer in terms of the gate oxide. They were then scaled down to gate oxide thicknesses down to a 1 nanometer thickness. At the same time, dopant concentration had to be increased in order to maintain gate control. But that was all successfully done over many, many generations following Moore's law and the reduction in these feature sizes, they introduced a lot of new materials. And with the new materials, new challenges, and we're going to focus mostly on the characterization and the modeling of these new materials in this presentation. So here you see, in this case, it's one of the parameters. It's the gate dielectric thickness, separating the silicon channel from the gate electrode. So in the early days, we were about 100 nanometer. It was scaled down to a few nanometers with 1 micron technologies, and then submicron technologies. It went all the way down to just basically 1 nanometer. And you see a transition here in terms of injection. In the old generations, you would go through Falden-Odenheim injection at high operating field condition or stress conditions, while in the very thin gate dielectrics, you have direct tunneling being the mechanism causing the leakage in the device. Now, in the sub-100 nanometer range, the gate dielectric was substituted with an alternative dielectric with a higher dielectric constant to maintain scaling of the CMOS technologies. And there was a very strong effort to replace the silicon oxynitride or SiO2 gate dielectric around 2000 with an alternate gate dielectric. And it happened basically in 2006, I think, at first introduction at Intel, or 2007 in their 45 nanometer first successful commercialization of high-K dielectrics in CMOS technologies. Now, what were the enablers in technology scaling over the last decade? Actually, it's now last 2 decades. Because it started around 2000, where we had 130 nanometer CMOS technologies being developed or slowly moving into manufacturing, and then it went all the way down, and now we're talking about 4 nanometer, 3 nanometer, or the nomenclature of Intel is 20A or 18A, 18 angstrom type of devices. Now, in these earlier generations, it was not just sufficient to simply scale the device geometries to get more performance. There had to be found additional performance element to really increase the drive current of those devices to stay on the performance scaling path. So with 90 nanometer, the first introduction was the silicon germanium in PMOS devices. Let me do a quick poll. So who of you are familiar with CMOS devices? So most of you are familiar with CMOS devices. How many have experience with metal high-K CMOS devices? Quite a few less. So who has experience with, let's say, alternate device architecture like FinFET or fully depleted devices or ribbon type of devices? Even less. Okay, so I need to level set my pace going through this, but there's a good understanding on CMOS devices. There's some understanding on metal high-K and what is critical for future devices. So we have a lot to cover here in this presentation. Oh, so after the 90 nanometer with the silicon germanium enhancing the strain for the PMOS devices, the next was also strain engineering on NMOS devices, so liner techniques to keep on with the roadmap. And after 65, some folks actually still managed to deliver 45 with conventional polyoxynitride, but Intel went ahead with the first introduction of high-K dielectrics with metal electrodes in CMOS technologies. There's different integration schemes. Maybe we're going to have some time just briefly go over that as well. That one scaled for 2 generations, so 45 and then 32. You basically do the same to get more return on your investment and not have to bring up a new tool set for the next generation. After 32, the change was just simply scaling the dimensions with the high K still wasn't sufficient to get you beyond the 32 nanometer. So in case of Intel, the FinFET device architecture was introduced, and there are some other offerings where you have better gate control. In those nodes, they're also still being offered, so fully depleted SOI technology, for example, is also a contender in that 22 nanometer space. And going forward, we know the FinFET technology is used for several generations, and now in the next nodes ahead, it's gate-all-around device architecture, which is considered, which some folks call it ribbon-fed or just gate-all-around devices. So these were broadly the enabler for all the CMOS scaling over the past 20 years. Now, in the early days of CMOS, throughout this scaling, what were the critical reliability challenges? And some of you may not even have worked on or thought about these things being a challenge. For example, the early challenges was really ionic contaminations of the gate dielectric caused by alkali metals like sodium and potassium. Now, sodium is basically you sweat. If you would handle the wafers with your bare hands, you would introduce sodium, and that would give you all sorts of troubles in terms of stability of those devices. But it could also come from the tooling, that there is some contamination in the tooling, and you could get these sodium contamination. But basically, there has been a lot of advancement in the tooling and in the process that nowadays nobody really talks about alkali contamination in your CMOS flow, unless you have some excursion and some problem happened, and then you have to go back in history and say, what could it be? The next big challenge was scaling the supply voltages, and then hot carrier became a big issue for CMOS technologies. So nowadays, you still hear hot carriers being a concern, but back in those days, I mean, hot carriers were a real concern. And you could have a lot of aging in digital CMOS if you wouldn't have come up with all the innovations in that area. So for example, the lightly doped drain regions, that process was introduced to really mitigate all these hot carrier concern at around 1 micron type of the technologies. Now, when the gate dielectric scaled, and we showed that it was successfully scaled from 100 nanometer down to less than a nanometer, there were also issues in terms of gate oxide reliability, especially the extrapolation models. They were very conservative, and there was a doomsday scenario predicted, which actually didn't happen because the models got updated, and the introduction of, where are we here, power law models, they came to the rescue and provided sufficient TDDB reliability margin. The next issue, which came right around the time of gate oxide scaling becoming a big concern, the introduction of nitrogen into the gate dielectric brought bias temperature instabilities into the forefront, especially the PMOS device. So with the introduction of nitrogen in those devices, you had more positive charge build up in those devices and drift coming from potential hole traps with the introduction of nitrogen. And this nitrogen introduction was basically maximized to the extent that PTI becomes a real limiter. This one didn't really go away. It's more modeling effort, better characterization. Some of it is just how you account for it in digital CMOS. The devices are switching. They're not in a static operating mode like they are done very often in the device characterization or in the aging characterization. So the PTI mechanism remains a concern today, and remains a concern for till the end of, I shouldn't say the end of the roadmap, but in the foreseeable future with the introduction of the gate-all-around devices, PTI instability remains a concern because it limits basically how much you can scale these dielectrics and improve your gate control, improve your performance. So in the real classical case of reliability performance trade-off. And the last one was the introduction of the high K dielectrics. And that one really around 2000 started the industry-wide collaboration, Sematech, EMEC, working together with a lot of member companies having their own assignees. Myself was working on that as well. And it was a huge effort to first understand what the issues are and come up with potential solutions for the instabilities. And I think I can steal the thunder here, but it's basically scaling the high K to the extent that you don't have a large amount of trapping. That was basically one of the directions to go. And the other is to maintain an interlayer thick enough so that you don't run into other issues. Okay, so let's now dive a little more into introduction and then discrete devices. Yes, first the introduction. Just a few words of what we're going to talk about. The first mechanism we're going to cover is dielectric breakdown, or TDDB, time-dependent dielectric breakdown. But we may just going to use breakdown as a short form. This is just a textbook definition of what it means when an insulator loses the insulating property. Basically, when you apply a voltage across, the current goes up, it starts to leak. Or when you inject the current, the voltage collapses across the insulator. That would be the dielectric breakdown. And it's a statistical process. So you have critical failure times. Viable distributions are basically used for all of that. So you have a beta value, T63, and that one scales with voltage, temperature, area, and percentiles. And it's all very well explained with the percolation model, which is basically just randomly forming defects in the volume of the dielectric. And then when there is a connecting path, that's when the breakdown event is triggered. The other mechanism we're going to talk about is the bias temperature instability in the CMOS devices. So the instability was known for PMOS devices, even with conventional gate dielectrics. But with the introduction of metal high K, you started also to see the instability in NMOS devices. So here it's a conventional polyoxynitride NMOS device. The thickness here is the typical 1.3, 1.5 nanometer thickness. So this is a pretty thin gate dielectric. You can go up to 2.5 volt, and you see very little instability. Well, if you change from polyoxynitride to metal high K, in this case, it's all hafnium-based dielectrics, but there were other contenders there as well. So the zirconium was one of the other contenders. There's aluminum was one of the other contenders. But the industry basically, at some point, decided, okay, go ahead with hafnia and make this happen with hafnia. Now, when you reduce the thickness, you see the instability quite dramatically diminishes. So if you have a 2.2 nanometer thick, I mean, that's not a thick film, but it's thick enough to give you quite a lot of instability. If you just reduce it to 17 angstrom, then the instability quite substantially reduces. On the other hand, on the PMOS side, it didn't really matter that much whether you have a high K on top of an interlayer compared to the NMOS. And just a word on the stack itself. So you have the silicon. Then if you talk about a replacement metal gate process, so you typically have just an interlayer as an oxide. So this is an SiO2-like interlayer. Then you have a hafnium-based dielectric on top, and then you need the proper metalwork stack to give you the right threshold for NMOS and PMOS devices. So you see NMOS and PMOS just altering here in terms of work function material. So this is easy to draw on PowerPoint and say this is the NMOS material, this is the PMOS material, but it's actually pretty difficult to integrate in a CMOS flow because you may have to deposit in one case, you may have to etch it off in the other case, so the integration can be fairly complex. But this is how typically these high-K dielectric stacks look like. Another remark is there was very early a strong desire to scale the interlayer to 0 interlayer. But 0 interlayer would have put the hafnia right next to the silicon, and you could see what kind of troubles you may get into. Because if you don't have the SiO2-like interface, the device characteristic very rapidly degraded. So you may find them in research papers, but in industry you don't see really 0 interlayer type of CMOS devices. Another big issue which was reported on for the negative bias instability was the recovery effect. So if you apply stress to the device, you shift the VT, you take off the stress, you just ground the terminals, for example, then you see that some of the instability recovers and it goes back and forth and just progressively increases with prolonged stress time. So that has caused a lot of early confusion and then a lot of desire to minimize the recovery. So a lot of effort was made to improve the characterization so that you can really capture the worst case. So, but the same is also seen for PBTI. So in metal high K with the NMOS device, you have the electron trapping, you take off the bias, some of it recovers, and then progressively gets worse. And this is pretty similar in nature in terms of what the kinetic is, even though physically the defects may be quite different. And of course, the question is always, what is the impact on these logic devices when you're subjected to recovery? Another word on the methods, how to assess these various mechanisms. I mean, the reliability studies are typically very time-consuming. You need a bunch of samples, you need different stress conditions, maybe you have to change the ambient condition, so it's very time-consuming. And in old school, you would say just apply the voltage and measure as a function of time. And you can do that for the various mechanisms. Here's TDDB, BTI, but there's also hot carrier or non-conducting other stress mechanisms as well. So you would do it in that fashion. Now, in the early days of really research in high K dielectrics, it became clear that I cannot spend so much time on each and every process split. So I need to accelerate it and come up with some sort of an assessment which gives me more rapidly a feedback whether I'm going in the right direction or in the wrong direction. So we applied then basic models that you say, oh, there's a known model for voltage dependence and time evolution for TDDB. You can translate that into a model if you do a linear voltage ramp, and you can come up with correlations, and actually they turned out to be not just qualitatively explaining it, but actually quantitative explaining it. So the parameters you extract with one method, you can translate into the other method. So it was very helpful for TDDB, and with TDDB being a statistical process, you need a pretty substantial sample. So it was very helpful for TDDB, but also it helped us with narrowing down choices in terms of process option for bias temperature instability, because you can go through the same exercise. The exercise is a little more complicated because it's a sublinear time dependence. Am I running out of juice? No. Huh? That's, yes. So you can do the same exercise with the BTI mechanism, and you have the equations here, and you can go into the references if you're interested in how this was derived. Oh, this is
I think we're running out of batteries. So
okay,
please.
so this is,
Yeah.
it wasn't feedback, or?
Sorry.
It wasn't feedback.
Yeah, right.
Okay. So here you have the equation. So throughout you may see in some cases the VBD or parameters from one versus the other used just to illustrate what the impacts are. Another, did I turn this on? You guys can hear me, right? Yes. So the other one is the fast characterization. Because of these recovery effects, the whole industry wanted to minimize the delay so that you're actually measuring a large amount of the degradation, not just the small amount of degradation. Because if you're in reliability, you may also be in liability. So if you're in liability, then it's a lawyer talking to you. In order to make sure that you're not having a problem, you can also make let's say an optimistic projection. And these delays impact your model parameters. So in one case, the model parameters will lead to conservative projections. In the other case, a little more optimistic projection. And that's why the whole reliability community was, let's say, banging heads quite heavily to sort out how much delay is tolerable in order for you to claim that you actually have something, very useful. And it boiled down to, originally, this is around 2010, that fast BTI characterization should be sufficient to do all of that. With fast BTI characterization, it's basically trying to measure something with millisecond delay. While later on, there is also an effort to say ultra fast, and instead of milliseconds, you say now microseconds. But in many cases, it doesn't make that much of a difference anymore between millisecond or microsecond. But just that you're aware, there has been a lot of discussion in that directions. What is the right sense time to use in order to capture the PTI instability? Now, in general, what you do is you do a time zero characterization of your devices, then you subject them to a stress, and then you go back and you do a diagnostic measurement. Now, nowadays, you still see folks that, since they have instrumentation which can do it much faster, that they would do not just an interim spot, but they may do an interim full device characterization. So that's, I think, up to everybody to decide how much of the hard-earned bandwidth I going to use for doing a full characterization versus just doing a spot measurement. In my opinion, a spot measurement should be sufficient to establish the kinetic time evolution, and if you need more detailed device characteristic, you can always do a post stress characterization to determine all the parameters like the subthreshold degradation, VT shift, GM degradation, linear degradation, and all those various parameters. Now, in most of the cases, you can then monitor either in the saturation regime. A popular one is just the IDZ, where you have a high drain bias and a high drain and a high gate bias, so you measure the saturation current, you're monitoring the saturation current as a function of time. The other one, you could do linear current, can also potentially be beneficial. We may have some discussion tomorrow in a presentation I have prepared on the ring oscillator characterization, that there's some, let's say, different observation you can make there. Or you just monitor around the threshold. Now, the current degradation metric is very useful if you're interested in performance and speed. So a lot of folks would just use the current degradation metric as the right choice. While if you're interested in stability, memory, SRAM, you may actually choose a VT metric, because you're very sensitive to VT of individual devices to ensure that you have the stability of your circuit. But these are the two common metrics to compare. It's either current or voltage shift. Another topic which is coming up more in the future nodes, so we're not going to discuss a lot of it here, is the self-heating effects, and I should say the self-heating effects in bulk devices, because self-heating was known to the SOI community that self-heating is just something you have to deal with. You need to do proper characterization and just account for it. But when the big players came in and developed bulk FinFETs on bulk silicon, then they say, oh, now I've learned something I haven't seen before, and for them now bulk self-heating became a big concern, and they kind of really, they were beating the drums so that everybody gets to hear, yeah, pay attention about self-heating, and it's definitely something you need to pay attention to. But I think it's just an engineering challenge you need to work around. I mean, if you can't have that power density, you need to give that more real estate, and you should be able to mitigate the self-heating. So in our case, when we looked at this, I think it's 40 nanometer, a typical hot carrier type of test conditions. So we have here the power per fin versus the temperature rise in the test structures. You see we raise it by 25 degrees, but it's at a high stress condition. So it's a noticeable increase, but it's not a devastating situation that in some cases you may find in SOI that you are able to heat the device by 100 or 150 degrees if you really pump the power through. Typically, the way things are done here, you have some sort of heater sensor configuration. First, you would have to do a calibration on the sensor. So if you use the MOSFET, then you use just the temperature sensitivity of VT as your sensing characteristic. You do a calibration of that, and then in the next step, you would just turn on the heater devices surrounding the sensor, monitor the power dissipated, and then correlate it with the temperature change. First, the VT change you see, and after the calibration, you can use the VT change to change it to a temperature change. And this is basically what is shown here. This was some early results we've shown, but we have basically used all sorts of sensor configurations, which are the a MOSFET as a sensor surrounded by heater. We also have used gate Kelvin probes on the MOSFET device, where you just use the gate sheet resistance as your sensing characteristic. There, of course, you don't have to worry about the heat transfer from the adjacent device into the device. So here you can really measure with the gate Kelvin resistance the temperature of the device when power dissipation occurs in the device. So that actually brings this characteristic up by a noticeable amount. So it's a 50% more roughly what you see if you sense with the device with the gate resistance compared to the adjacent device to a heating element. And if you use, for example, a diode as a sensing device, then it's no different from just using a MOSFET device. And you can use the diode in the forward characteristic, revert characteristic. They all show temperature sensitivity, and you can just use those for characterizing self-heating. But as I said, it was a moderate rise in 14. It's going to be a little more of a concern in the next generation nodes, but the amount of publications on the topic is not exponentially going up. I think it kind of plateaus because folks realize it's just an engineering challenge, and it needs to be captured by thermal models as part of your design flow. The other thing I should point out is with these sensor structures, you can only do so many on silicon. With a simulator, you can simulate any case. So the sensors and these structures are only there to calibrate your simulator, and after it's calibrated, you pass on the ball, and the next one can do the job to ensure that you're not going to have any thermal issues. Now let's go a little bit more into detail with TDDB first. So when we started the development of the first commercial process, it wasn't clear what kind of a figure of merit should apply with high-K dielectrics. So the two popular choices you would see also from conventional polyoxynitride technologies is using the capacitance or using the leakage. Now capacitance in a dual layer stack can be just a combination of K values and thicknesses of 1. That didn't really provide a good correlation. But when you just take the leakage itself and use the leakage and correlate it with the failure time, then we had a very strong correlation. So after the first generation, then the next generations, the figure of merit was just to compare where do you stand with your failure times in terms of leakage of your structure. Because if you just go along this way, then you are going along, let's say, in a known path. But what you want to have is low leakage and long failure time. So this is the area you would want to be if you really try to outperform the previous generation. But in many cases, there was nobody outperforming anybody. It was just a game of interlayer and high-K layer thicknesses, and you would just walk along this line. There can be, of course, also the other case that is, hey, you make things worse. And that would be low leakage and short failure times. So if that one, these are obviously, these you weed out because that's not improving your process. So it's either along the line or in this corner if you want to have a superior process in terms of TDDB performance. Now the other aspects were then going into the modeling and projection. So the one thing, when you change from polyoxynitride to metal high-K, on the NMOS side, the leakage went up dramatically. So with a dramatic increase of leakage, failure times got much shorter. So with the shorter failure time, and let's say conservative models back then, let's say exponential models for projection, there would have been a real problem demonstrating that this is actually viable to be used in CMOS manufacturing. So the one thing to first we checked is just the voltage dependence. And around that time, the power law voltage dependence for TDDB has become not just popular, it was basically the one to use for the projection, because the exponential models, they had this doomsday scenario predicted, which didn't occur. So power law was well accepted. Now the only thing was to demonstrate that actually the acceleration factor is significant or high. And in this case, we have a wide voltage range going down to less than 2 volt, a power of 55, which is on the higher end what you typically see also for polyoxynitride cases. So the power law acceleration was pretty healthy. So that wasn't a concern. The other one done was to project to low failure percentiles or large areas, which a CMOS product would naturally be. I mean, you're not selling a tiny little chip, except if you're doing a RF power amplifier. That one is not that big, but if you have a huge logic processor, then you're in the millimeter square or tens of millimeter square of gate oxide area. And that would show up on the TDB failure distributions here. Very low in percentile. So the larger the area, the shorter the failure time, and the lower the percentile. So when we started looking at the early processes and looked at small area devices, we always had pretty conservative viable distributions till we started exploring to larger areas and noticed there is a transition. And incorporating this transition from a shallower viable slope, which gives poor projection, to larger viable slope coming from larger areas and tighter TDB failure distribution, we had at the end sufficient margin for first introduction of those into some commercial products. This was just the experimental observation, but then there was a slew of efforts to understand what's behind these observations. And Tanya Nigam from Global at that time, she worked on percolation models before for polyoxynitride. She basically now diced it into 2 layers, that you have an interlayer and a high K layer, and with competing degradation rates in these 2 layers, you can actually explain a transition in the viable slope for a shallow viable slope at the high percentile versus a steeper, tighter distribution at the low percentile. What it basically means at the end is if you're at the high percentile, one of the layers is actually fully defective, and you're just waiting for a thin layer to fail, and the thin layer naturally has a lower viable slope or a wider distribution. Well, if you're in the low percentile for a large area structure, it becomes more of a random event of both layers then connecting, and at that time you're going to get the benefit and the increase in the viable slope. Around the same time, EMEC also made efforts to explain their observations. In polyoxynitride, there was a known phenomena of progressive failure, where you say there is initially a small leakage current. The leakage current evolves as a function of time and increases, and with that you can also have a similar explanation in terms of the viable distribution. And the last one here is Jordi from Barcelona, and together with IBM, they basically say, hey, if one can explain, the other can explain, a combination of 2 most likely can also explain it. And that's basically, you have now competing degradation of a 2-layer stack and the progressive wear out. But basically it says everybody was looking in the same direction, trying to explain it, and there's a lot of understanding on the TDB failures in the first generation of metal high K, and that's why it was initially a concern, and now it's just something to manage and to benefit of the fundamental understanding. Now let's move to the PTI mechanism. Here we say in PMOS devices, the conventional stack only has a thin Si 2-layer. Now you're adding high K on top of it. Most of the action actually happens at the silicon interface, so adding high K to it didn't really significantly alter the observations for NBTI. There's another caveat for the folks. There's the difference between the replacement metal gate and the gate first integration in the CMOS technology. So with a replacement metal gate, typically you have it on the silicon channel. The gate first integration, in order to adjust VT, the interface wasn't really silicon. And you have to dig in the literature to find out the right paper, but it's a silicon germanium interface. Now silicon germanium had some benefits in terms of NBTI instability. So for the gate first integration, the PMOS device was really not, NBTI was not the concern. In that case, it was PBTI. And PBTI is now, you have this interlayer, and you have the high K layer, and you have basically electron injection into the layer. You have plenty of defects. If you make that layer thicker, you get even more defects, and you can, like a sponge, fill them with a lot of electrons and just shift VT to concerning high levels. Now, so the original explanation was that oxygen vacancies could be the source of the defect. But the other thing also is with a high K layer, which has a much higher dielectric constant than the interlayer, in terms of energy, this defect band moves pretty rapidly. So if you stay below, you don't inject, you don't see much of an instability. But if you start injecting and you're moving these and you fill them with electrons from the inversion layer, then you can have pretty huge instabilities. And I would say the classic picture didn't really change over the last 15 years. So the only thing which changed from the early days was this layer got thinner. But some folks may also have said the layer got actually better. Got better as well, but I think mostly it's just making it thinner with, of course, the process control at these thin layers so that you're able to make, let's say, a less than 20 angstrom thick high K layer on top of a thin interlayer, that actually worked at the end. Now these recovery effects shown here again. One of the first nice experimental demonstration was actually Reisinger on a polyoxynitride stack. That was, I think, as I said, 2006. So it was about the time I was at Infineon. So I noticed or firsthand experienced his effort there. So he stressed at fairly high voltages, increasing stress time, got more instability, and then he basically monitored the recovery of the VT shift by in-house or home-built test equipment. So he had his own test circuits, and he could do microsecond delay measurements and monitoring the recovery of those devices. And obviously you can see typical test equipment back in those days, they would have taken maybe a second. But I don't know if there are that many old school folks here. So when there was characterization done in the old days, it wasn't a spot measurement and say, oh, I want to measure a VT shift or I want to measure ID Lin degradation. It means you have stressed the device and then you went in and you did the full characterization of IDVG, IDVD, various conditions. So it takes you minutes to take all the data just for one stress interval. Now, of course, if you do that, then you have more of that instability, and that's why a lot of folks, let's say, cried out foul. They say you can't do a full characterization with a lot of delay and then tell me you don't have NBTI concerns. So this paper then showed, oh, okay, if you do it ever faster, this is a log T dependence. It just gets worse and worse because log T doesn't go forever either. But at some point, it would say that's where it really starts to. And he could show a microsecond in his case, almost needed to show a good amount of the degradation. So we did the same then for metal high K stacks, PBTI. You also see log T dependence, but noticeably it's not as steep as what Reisinger saw in his cases. And in hindsight, it's pretty obvious because if this one is very close to the interface, the response is much faster. If the high K defect is a little further from the interface, the response gets slower. So this rate of recovery don't necessarily have to be the same. So for NBTI, you got to be a little faster than for PBTI. Now, this is just to fill in the gap because we said before there is fast and ultra fast. So the 2 millisecond, that was what JDEC proposed in early 2010, around that time frame, being sufficient. And actually 2 millisecond is also convenient because you don't need the most expensive equipment to do that job. But nowadays you can get instrumentation where you can do much faster than 2 millisecond. But we just tried to show that actually if you measure long enough, it doesn't make much of a difference whether you do it ultra fast or fast because it's almost like a constant offset. And this comes out of the mud on a log scale. So as soon as you're out of the noise, then adding a few millivolts is not going to make a huge difference. So it doesn't make a huge difference in terms of voltage dependence, but also not a huge difference in terms of time evolution. So in our opinion, it's a millisecond good enough. If somebody wants to do microsecond, of course, there are a lot of free countries you can do so. So there's no restriction to that. You can do 10 microseconds as well. On the PBTI side, really the knob, I kind of hinted to that before, the knob was really scaling the high K thickness to a minimum level so that the stability kind of is low enough so that you can live with that in terms of a circuit, from circuit implementation. If you would go back and say, okay, I'm going to do another 5 nanometer thick high K on top of an interlayer, I want to sell a CMOS technology, I think it would really be an uphill battle to get that out the door. With no amount of process improvement, I think 5 nanometer is going to be feasible. So scaling was, I would say, one of the big knobs, beside process control and improvement in general, helping to be able to fabricate these thin films. Another big change was going from planar to fin architecture. So in planar technologies, it was basically PBTI being worse than NBTI. Okay, so this is the bulk planar, the PBTI. And then moving to the fin technology, you got almost a 10x improvement or 7x improvement in terms of PBTI, which is huge. I mean, instead of 100 millivolt shift, you only have 20 millivolt shift, and somebody, that's a huge benefit. On the other hand, on the PMOS side, it didn't get better, but it just got slightly worse. So overall, nobody was standing in the way of transitioning from planar to fin. I mean, reliability wasn't the first one to make a case anyway, because it was not possible really to do further scaling in planar in terms of delivering a process with sufficient SRAM V min margins and in a planar technology. But the reliability could be managed by huge improvements in PBTI and just a minor increase in the NBTI. Now, how does this typically look in a circuit or in a simulator implementation? So you have these models. The models are mostly sublinear in time. This is for PTI, so the time evolution would be maybe somewhere between 0.15, 0.25 time evolution. Then you have a voltage-dependent factor. The voltage-dependent factor can be either power law or exponential. That doesn't make much of a difference unless you extrapolate to very low voltage conditions. And then the question is what your metric for comparison is. The more advanced nodes, they mostly use VT as a metric for comparison and less ID set. And there may be some political reason to that. I don't think I want to go into the details there. But in the old days, they were basically, one foundry supplier would provide ID set as their metric, and the other mainstream suppliers would have VT. But with the move to fin, they kind of all converged to VT. I mean, at the end, it's whether you do VT versus ID set, they got to be correlated anyway, because otherwise you would have difficulties with your implementation in a simulator. It's just a matter of question of which one do you extract first, and the other one you just extract through correlation tests. Now, when the devices in these advanced nodes get small, then this PTI, but also the hot carrier, they just become now stochastic processes. And with all the stochastic processes, the pain just goes up because typically you need more data to collect in order to validate and demonstrate your models. Now, if you think about the two main, let's say, digital blocks, let's say logic circuits, like an oscillator, what would be the most concerning aspect? Is it the mean shift, or is it that the variation between the devices and the variation in the shift between the devices, which is the big concern? So in my opinion, for the oscillators, where you still have tens of devices, because the chain, you have maybe 10, maybe good number of stages connected, it's the mean shift which really dominates there, and it's not that variation yet. But for SRAM devices, that's just the single unit 6 transistors. There it's really the variation which is the biggest concern, in addition to the mean shift. So for the SRAM devices, you really need to get to the sigma of your variation accurately. And that's where we have put some effort as well. So this is now just a basic model for the PTI instability. The typical parameters, as I said, 0.15 to 0.425 for the time evolution. These power law dependencies, let's say for MBTI, it's 3.5 to 6, but you can always translate them to exponential models as well. So this is just a reference here. For metal high K, typically the voltage dependence for PBTI is a little larger than NBTI, and I think it's just the nature of the dual layer stack and how the defect band moves in energy. So when you drop below, it dives off more rapidly than it does for the MBTI. And the temperature effect, that's just an Arrhenius with typical numbers of 0.1 to 0.2 EV in the delta VT versus time domain. Now, another important aspect is not just this DC type of aging in discrete devices. How does it really now impact the digital circuits? And what can you do on discrete devices to mimic what happens in the discrete circuits? So in the DC stress, you would only do the stress and these periodic readouts, but you can now envision also doing other stresses to discrete devices to get additional information in terms of recovery when you just alter the gate potential, or recovery when you bring up the drain and keep the gate low. So this is like an inverter type of stress scenario you have in a simple inverter or in the cross-coupled inverter in the SRAM cells. So there is also quite some effort on the discrete devices to better capture these recovery effects. So the first thing we looked at was just purely the frequency dependence, and over a wide range of stress frequency, you see this is going from sub-hertz, so pretty low frequency stimulation, to 10 kilohertz. That's something you can easily do with these new commercial instruments. There's very big frequency dependence in terms of NBTI. And also this is just now the remaining shift measured with an AC toggle on the gate compared to the DC stress. So you see roughly half of it recovers. Now for the PMOS, the NMOS device, there is a difference between the gate first planar versus the replacement metal gate fin. So with replacement metal gate fin, there's a little less of a recovery you see from the electron trapping. One reason could just be that the interlayer a little thicker. So now the communication, the chance for the electrons go back to the channel is a little lower after they get injected, while the gate first was a very aggressively scaled NMOS device. So the interlayer is very, very thin, and now you have better communication and you have more recovery in those devices. But in general, you just need to be aware that there is recovery, and you can incorporate that for the digital CMOS applications. The impact, whether it's an AC or inverter type of operations on the PMOS, it didn't really make much of a difference, whether you just bring down the gate to ground or you bring up the drain from 0 to VDD. It didn't lead to extra recovery, while in the case of the NMOS device, there is a small dependence there as well. Now let's move to the stochastic process. So stochastic process basically making a large device now smaller in order to get the same mean VT shift. You have here more number of carriers involved in the instability area, smaller, and points out basically tells you how much variation you should expect. By reducing the number, naturally the variation goes up. So you can have cases virtually there's very little shift, and then you have cases where there's very large shift. And that is a big concern, of course, for the SRAM devices. There's some test structure innovation in doing that stochastic assessment. So back in the old days, you would just do a single device, and you would change the width and the length simultaneously to make a device larger. That one was popular for some time, but it became unpopular when the gate really got shorter. And you may have impacts, let's say, from the SDI and from the diffusion separately, and you don't want to scale just by width and length. So you would say if you want to make a device larger, you would just make it wider, but you have the same instant replicated a couple of times. So you would have a nominal device, maybe a sub-micron width, if you need a 10-micron wide device. So you have stacked 20 of them in the width, and that's how you would make a 10-micron wide FET. Obviously, there are limitations to that. So if you make it wider and wider, the current you need to measure VT also goes up with the width. So at the end, it's not practical to make a centimeter wide FET just to measure VT, because you have a lot of current you need to supply, and potentially contact resistance and all those sources coming into play. So another way of doing a larger device would be scale it in the width, but also scale it in the length. So you just place pixels and you wire them up so you can make a large device which mimics a small device and doesn't have that problem of a huge leakage. This is actually a very nice device to measure the mean degradation. And you don't need 20 transistors for testing. You can do, you should test more than one. I mean, the second one to verify that the first one is the same. It's the second one, maybe 3, then you have good confidence if they are all the same, then you have hit the mean VT degradation. This obviously doesn't work if you need to get to the sigma of individual devices. So in sigma for the individual devices, if you only have one device across a wafer, typically a 300 milli wafer gives you maybe 80 shots, you get 80 dies, 80 dots per wafer. That's not really sufficient. So you have to do some innovation there. We use transistor arrays where you can just scale them up 4 by 4, 8 by 8 to give you more samples across the wafer, where each and every device really has, where you have access to the device characteristic. So in this case, you can get the VT, the mean, but now you can also get to the sigma. And we have done a couple of those experiments as well and learned from that. Now, from modeling perspective, I hope that everything up front remains the same, and you will only have to discuss the percentile scaling or the variation component. Everything else should be the same. And choices, poor man's version of variation is just use normal distributions. They may be a little too progressive. So there are, in the industry, the compound Poisson process, Stu Rauch from IBM, he introduced that in 2002. There was no follow-up to that publication because everybody, it's like you read the Bible, you comprehend it, you do it, and there's nobody questioning and challenging it. So there was a long time nobody questioning and challenging it. And then EMEC also started looking into the problem of variation themselves, and they came up with a nuanced, slightly different model, but basically, very comparable to the IBM model. And what it basically says, these models, that the mean of the distribution, they're all described, adequately. It's where in the tail they start to diverge. So the data set we have here, this is, I think, a 3228 nanometer device type, the NBTI here. And I don't think it was the narrowest devices we had, but in this case, you see the normal distribution actually explained it right up to the 3 sigma level. And only beyond that, you could envision dispersion. So you see the green one, that was the IBM model. So the IBM model at 4 or 4.5 sigma, that would just be additional 10 millivolt guard band in your sigma VT variation. The EMEC model, Ben's model here, they show, depending on what the parameter set you use, if you say this eta value, which is the average impact of a charge carrier on the VT, if that one is low, then you actually don't see much of a tail in the distribution, but you're very sensitive to that. So if you say instead of 2, it goes to 3, then it becomes very noticeable there as well. But in general, if you need to go beyond 3 sigma, life gets complicated if you don't have either a shared gate device structure. This may get you to 3.5 sigma, but if you need to go beyond, you really need a variability test structure. And there are some cases out there in the literature as well where folks did a couple of thousand per site, and across the wafer you get to like megabit type of data for small individual devices. Now, I should say, we started discussing that in 2013. There was some other discussion around there as well. Most of the early discussion was you measure your device once, and then you say, okay, NBTI, PBTI happens, I remeasure it again. This is the magnitude of shift I see, and this is all coming from PBTI or NBTI. Now, if you go and you say, oh, I measured the device now twice, and I don't stress it, then what you make, and of course there's a lot of literature on that out there as well, you say there is potentially small devices having some stochastic fluctuation, you call it RTN. Now, if you have RTN sitting on top or below your BTI stochastic model, it just adds naturally to skew in the model. Now, we have done the exercise, this is just, I think, some time zero characterization for NPMOS devices. I think this was a 20 nanometer type of device. You have, I mean, this is a pretty pronounced tail, and you can explain this tail again either with normal distribution, or you can do some more sophisticated modeling, but this is a pronounced tail you have in these distributions. And since they're there, let's say, time zero, they're also going to be there then afterwards when you do the BTI aging. So some of the skews in some of the models may actually be coming from RTN type of events and not the classical NBTI or PBTI aging you would envision. This is now just a case where we have now the model, actually the data, then the Monte Carlo simulation for the VT shift, and then we add the RTN on top. And you see when the shift is small, then the RTN on top gives you more skew in the tail of the distribution, both for PBTI and NBTI. But when the shift gets large, then this RTN distribution becomes a less important factor, because the mean shift kind of overwhelms and the RTN doesn't increase over the age of the device. And after 2015, it's like somebody puts water on the fire. The fire has gone not out, but the fire doesn't burn as rapidly as it did before in terms of the stochastic variation and the impact and how to model it for these small devices. The other, I think, important aspect, unfortunately this is a little busy slide, but the important aspect was from moving from bulk to FinFET device architecture. So in order to keep gate control in bulk technologies, doping had to be pretty high. And with high doping, you have a lot of stochastic random dopant fluctuation, which is the same as stochastic variation. So in small devices, you have a lot of variation. Now, when you move to the fin device architecture, you could take out that additional doping in the fin devices, which increased the threshold voltage variance here by a noticeable amount. So between 28 and 32, down to fin, there's almost, now I have to see here, this is a 3 or so X improvement. So this is a pretty substantial improvement. Now, on the other hand, the PTI-induced variation, which is a pure number fluctuation in the device, which comes either from trapping in the high K or from the interface, that one didn't really change, going from planar to a fin architecture. And obvious, I mean, it's pretty obvious why it didn't change, because we didn't change the oxide thickness either. So you're very aggressive, same aggressive gate oxide. So this didn't change. This one improved. Now the relative importance of the PTI-induced variation with the low-doped substrates is just went up, unfortunately. And that's just something you have to capture in your design. So there's no way out here. So nobody's going to put in doping in fins just to make them at time zero bad, so that the RTN-induced variation would not be such a contributing factor. I mean, this applies to fin architecture, but fully deviated devices where there's no doping in the bulk either. That would be the same story there. That the variation now becomes more of a factor and needs to be accounted for. I think for the sake of time, I'm going to skip through these summary here, and I want to go to the circuit characterization, and in particular, ring oscillator degradation. So all the effort so far was done for discrete devices, and there was a huge effort to minimize the delay from seconds to milliseconds to microseconds. And there wasn't the same effort for done on oscillator circuits at the same time. And that's a good question, why? So we did an effort then with all the new instrumentation. You can implement a fast PTI or a fast ring oscillator measurement the same way you did for the PTI aging. And the trick here is just use synchronized power supply switching. And this synchronized power supply switching was also needed to do a fast PTI measurement, but that was implemented by the tool vendor. So now you can use the tool and just adapt it and do oscillator frequency measurements. And this is just an example. So in our case, you have odd number of stages to give oscillations. So typically the n is an even number, but the enabled state adds another number. So for standard process variation, you would have a 100-stage oscillator. Actually, it's a 101-stage oscillator running. You have your own power pin for the oscillator, a shared ground. And then you have a peripheral circuit which divides the frequency, because you don't want to measure gigahertz frequency directly off an output stage. Then you would have a huge overhead. So typically you have a divider that can be anywhere from 8 to 14 stages dividing the frequency. In our case, often 10-stage divider, so a gigahertz comes down to a megahertz, and a megahertz you can easily measure with the scope. And here you see a burst of signal. And with the advanced scopes, you get all the statistical information on the signal, the mean frequency, standard deviation, min, max, and all the good stuff. The option here you have in most of the designs that you can do either enable high, which means the oscillator is running, and here you would trigger the capture just by triggering the divider voltage from keeping it off during the stress and just turning it on during the readout. So it's basically self-triggered after the scope is armed. You just receive the signal, you get the information back. Or the other option, you can also have it in a static mode, and you can compare the static arrow aging with dynamic arrow aging. So in the old days, you wouldn't do static arrow, only dynamic, because you wanted to use it for hot carrier characterization anyway. So in most cases, it's only dynamic arrow degradation you would capture. But since we have this discrepancy with recovery and in general static and dynamic input, we always focus on both static and dynamic operation. And the first exercise then was just to capture, is there a frequency dependence of the oscillator degradation? If you in terms of NBTI, you wouldn't expect any frequency degradation. So you see that over NBTI and PBTI, so over a wide range, there's no frequency dispersion here in the degradation. But they differ between static and dynamic. So in this case, now I have to static blue. So static often has a higher level of degradation compared to dynamic, and that's because recovery is built in under dynamic operation. So if you're concerned about the circuit, in your case not switching at high frequency, switching potentially at low frequencies, or being in a static mode, then you would be concerned about static aging as well. And this applies two different designs, two different test vehicles, different frequency range. They don't perfectly match up here because they're not the same design, the same process vintage, but you have no frequency dispersion. There is some literature out there which may say, oh, there is a dispersion, but in case of the ring oscillator circuit and also the discrete device circuit we measured, there was not much of a dispersion we observed. Now, the idea was to use the oscillator not to capture the PTI, it was really to capture the hot carrier. And the first attempt was in a polyoxynitride technology. So this one, I think, was at 125 C still at high temperature, and we just progressively increase the supply voltage. And you see at the low voltage corner condition, you only have a shallow time evolution. When the voltage gets high, the time evolution actually changes from shallow to steep, and that's the fingerprint of hot carrier degradation. So we didn't discuss the hot carrier model, but the hot carrier model typically has a steeper time evolution, higher power law factor compared to the NBTI. And this is really the fingerprint transitioning from NBTI to hot carrier aging. That was the easy case. It was with polyoxynitride, didn't have PBTI. Now, PBTI made it more difficult with the replacement metal gate FinFET devices. So at the high temperature corner and the low operating condition, it looks like it's all the same. It's a shallow time evolution, which basically means there are no hot carrier present in those devices. Now I have to see, actually that's not the case, but the slide is not in here. So if you go, you lower the temperature. Now let me see if the slide is actually here. No, the slide. So if you lower the temperature, And you further increase the voltage, and you can see the same what you see here, also you see there. But it's not a straightforward task to do that. So you have to really dial in the conditions so that you can see the transition from hot carrier to, from NBTI or PBTI to a hot carrier. Now, the one thing I wanted to show is in terms of self-heating, we have actually evidence, since we have had access at those days, both to bulk FinFETs, which still have a thermal conductivity to the substrate, and also the SOI FinFETs from the IBM technology. We could actually monitor and now check both. First, the bulk fin. So we have 13-stage and 101-stage oscillator. So the 13-stage oscillator has more power dissipation than the local power dissipation than the 101-stage oscillator. But you see at short times, there's no difference between the aging for the 13-stage and the 101-stage oscillator. And only at the long times you see, due to the hot carrier in the short stage, you see now an increase in the time evolution. But at short times where the PTI mechanism is dominant, the aging is the same, which basically means this is actually a pretty high stress condition, about 2x VDD, high power dissipation. Still, you don't see a difference in the degradation in the bulk fin. So you don't see any here. But now in the case for the SOI FinFETs, we still have the 13 and the 101-stage oscillator. So in this case now, the 101-stage oscillator actually shows less degradation at short times, while the 13-stage oscillator shows higher degradation. This 1.75x factor, if you translate it into a temperature rise, it actually suggests that at these high stress currents, the temperature goes up by 30 degrees for the SOI fins, while the bulk fins exhibit exactly 4x less. So now you do 30 divided 4 is less than 10 degrees, and less than 10 degrees is very difficult to capture here for the bulk fins. So there is a small increase here, but not really noticeable in the oscillator degradation, while the SOI fin shows that. And I think, in my opinion, all the self-heating, this is not the advanced node, but with the progressive increase with the nodes, may now slowly approach these SOI fin levels in 14 nanometer. And I think this is as hot as it's going to get in midterm for the circuits. We also used the oscillators to look at breakdown. So we went through VBD scans, both static and dynamic mode. Look at the supply currents, but also at the frequency change. So the frequency change wasn't a really good metric to look at ring oscillator degradation because it's kind of erratic, while the supply current was a better indicator. And in case of the static oscillator function, you see that the models coming from the discrete devices is right on top of the oscillator devices. So in the static operation, the DC models exactly explain what happens in the oscillator circuit. The situation is a little different when you do static versus dynamic. So here you have static. Here we have now different ring length change. So that one kind of validates the Poisson model. So the Poisson model applies very well, and only the very large areas, they don't follow. But they don't follow because the leakage into those oscillators is pretty severe because the change is very long. And it's the same not only in static, but also in dynamic. You see here this deviation. But more importantly, now there's a difference in the VBD value, which basically means when you run at high frequency, there's a little more life in those oscillators compared to a static mode. And currently, there's quite a bit of debate, discussion, whether this should be leveraged and CMOS technology is qualified to a AC spec versus a DC spec. So this just brings me to the summary here for the circuit. So we have this frequency independence in PTI. I think that's an important one to take home. There's no dispersion from sub 1 hertz to gigahertz based on discrete devices and oscillators. At short times, elevated junction temperature, PTI, dominates everything. And if you reduce the temperature, you may also be able to see some of the hot carrier signals. But it gets more difficult to demonstrate because you need pretty high voltages to do that. Now, the outlook, I would say the fundamentals of both TDDB and PTI, they're strong, and I wouldn't expect them to change as long as you don't change the substrate material. So as long as you stay on silicon. If you're talking about 3.5, then I would say all bets are off, but I don't think that many folks are talking about 3.5. FinFETs, FDSOI, so gate all around, it's all good. Further scaling the dimension, time zero and aging-induced variation, that's going to be in competition, just something to account for. We haven't spoken about the gate to contact, but that's another area where there's a lot of focus in terms of TDDB. And self-heating, that's just a growing concern, and particularly the gate all around. And at the end, having good correlation from your discrete devices to the circuit, that's always beneficial. But that's not maybe not an easy area where folks in academia or research centers can make a lot of contribution, because you need access to relevant technology. That's all I had. Thank you for your attention.
I can speak loud. Can you hear me? Yeah, great. Well, we are a bit short on time. We are a bit behind the scheduling, so I have time for one question. Yes, you are. Okay.
Oh, I take more than one. Oh, yeah.
I will do my best. Because this one will not reach the...
No.
So let's see if this one recovers.
Well, it may have recovery effects.
Okay, anyway.
Yeah.
Okay, now
So, so you comment on the using multi-layer oxide structures that you have progressive degradation. And in some of your slides, you show a picture where the degradation is a little bit more harder in one of the layers than the other one. Yeah?
In terms of just modeling, there is, let's say, dual layer percolation, just random in both layers. The others say, okay, there's kind of a seed, and after the seed is formed, it grows, and that's how you would call it progressive.
Okay, then.
But this is all belief, yes.
Okay, well, then
because it's model.
What happens if you apply the stress in a different way? Let's say that the device is on or off. Then, so the degradation is expected to be different if you are...
The simulations, they don't consider recovery for TDDB. So that's just the DC state. But if you say there is a recovery, then there are lots of questions, because defect formed, defect may be charged, maybe defect losing the charge. If defect gets charged again, is defect where it was before? There's a lot of, but there's no AC TDDB simulation I'm aware of. Folks would actually say, oh, it's first the defect, did the defect get formed? Was the defect there in the first place? Did the defect get charged? Did charging the defect cause structural relaxation? Is that now what you call defect being formed? There are a lot of questions, and it all goes into the assumptions of a simulation. And the simulation just says, oh, I plug in a rate for one layer, a rate for the other layer, and I end up with a transition. And these Monte Carlo simulations, they have been verified by others as well now. And they can predict the transition, but what it actually means physically, that's a good question.
Great. So it is an exciting subject. I do apologize because I have to interrupt the presentation to go further in the session. And then it closes our mini colloquium. I would like to thank again Andreas for your very nice presentation. I would like also to thank you all for staying till the very end. Let me just remind you that right away after the end of this mini colloquium, we will have the SB micro assembly, which will be in Portuguese, okay? And then right after, we will have the welcome reception. And also, I would like to remind you that tomorrow in the morning, the session will be in the Museum of Tomorrow, not here in this auditorium. It is right across in front of us in the Museum of Tomorrow. We will start with the plenaria at 9 a.m. tomorrow. in the auditorium of Museum of Tomorrow. Right? So with that, I thank you very much for coming for this mini colloquium, and I hope you enjoy the rest of the conference till the end of this week. Thank you.